Well, my friends, welcome back. Today we're going to take that big beautiful breadboard from the last video and we're going to figure out how the code works. Yeah, it's a one-way trip down a giant rabbit hole of complexity, but why not? You know, a wise man once said, real simplicity lies on the other side of complexity, or something like that. So buckle up, and if you need a break, don't worry, there's chapter links in the description. You can always pause and come back and watch your favorite parts over and over. But if you can get to the end, I think you'll find So if you followed the last video, then at this point you should have downloaded the code from GitHub, and I'll put a link to that in the description if you haven't. But when you open the code in the Arduino IDE, you're probably going to see something like this. This first file is the .ino file, and you can think of it like the main place where your program runs. For now, we want to keep this file as clean as possible because in the future we're going to add a whole bunch of stuff here, and we don't want to get it cluttered just yet. So to keep things tidy, we want to take all of the complexity of controlling the YM3812 and stick it in its own class. You know, things like chip control functions that are going to manipulate the sound processor at a hardware level, and register functions that make it easy to update specific global settings, as well as the settings for each of the channels and the operators on the chip. And finally, we've got a little bit of data storage. See, we can't read anything off the YM3812, so we've got to keep track of all of the register information as we go. And we'll do that in a bunch of register cache variables, and we'll talk about those later. One nice thing about this arrangement, though, is that if you wanted to use a different microcontroller, like a Teensy or a Nano, or even if you just wanted to swap the pins around, the only thing you'd really have to change are the two chip control functions, send data and reset. Everything else would stay exactly the same. Okay, let's dive into the send data function. On the left, we see the function's code, and on the right, we have the timing diagram from the first video. This will help us see how the code is creating the electrical signals that control the sound chip. We start by setting the chip select low by clearing the bit on port D of the microcontroller that it's connected to. We do the same to the A0 pin to put us into the address select mode. Now we need to send the 8-bit register address over the SPI bus to the 74HC595 latch. Then we take the latch pin on the microcontroller high, which makes the 8 bits of data visible to the sound chip, and then we wait a tick and then clear the latch pin. Okay, now the YM3812 has everything it needs to select the register. We just need to tell it to do it. So we clear the right pin, which since it's active low, writes the data, and then we wait a good 10 microseconds for the processor to catch up, and then we bring the right pin back high to complete the write cycle, and wait another 10 microseconds. Okay, now the register address is written, we set A0 high again, so that the sound chip knows we're writing data. Then we repeat the previous steps the exact same way, but we send the value instead of the register location. Okay, that's our send data function, and it updates an entire register byte. But it's pretty rare that we're going to actually want to update an entire register byte all at once. Usually the individual properties that we want to change are only just a few bits of that full register byte, and that's really what we want to update. So let's start with the easiest of these types of functions, a global function like vibrato depth. Vibrato depth is a 1-bit flag that determines how far vibrato is going to wobble the pitch. Since we only want to change 1 bit, we need to know how the other bits in the register are currently set. But of course, we can't get that information from the sound chip, so we're going to have to keep track of it ourselves in a register cache. Okay, so now we know it's in the register, and all we have to do is set the 6th bit that corresponds to the vibrato depth flag. And then we store it back in our register cache and write it into the chip. Easy peasy, right? Well, almost. How do you just set 1 bit of an 8-bit byte? Or if it's a 3-bit number, how do you set 3 bits of an 8-bit byte, or 4 or 5? Meet the setBits function. It takes a current register value and a couple of other things, a bit mask and an offset, and we'll talk about those here in a second. And then it stores a new value into the correct bits of the register value. Let's see how it works. In this example, we're setting the value to a 1, but realistically, we could just as easily be setting this to either a 0 or a 1. So let's change this to a question mark. Also, even though our value is just a 1-bit flag, it's actually stored as an 8-bit byte. And this is important because there's nothing that actually stops us from accidentally adding rogue 1s where they don't belong. So the first thing we need to do is mask out everything except for the 1 bit that we're interested in. and we do that with a bit mask. The bit mask is another 8-bit number that has zeros in all of the bits that we don't want, and ones in the bits that we do. This way, when we logically AND the two numbers together, any bits that have a 1 in the bit mask pass right through, and any that have a 0 will always be a 0, even those rogue ones. For this to work with larger bit values, we can just add more 1s to the right side of our bit mask, and that allows more bits to pass through. Okay, now that we know the value is truly a 1-bit number, let's set it aside for a moment and look at the register value that we want to put it in. This value comes out of our register cache and represents the full 8-bit value that's currently stored in the YM3812. Most of the bits in this value relate to other properties, so we don't want to affect those at all. But what we do need to do is create a hole of zeros that we can stick our new value into. And to do that, we need that bit mask again. Okay, clearly we're masking the wrong bit here, but that's okay. We can shift over to the left using the shift operator. And if we left shift over by 6 bits, then just like before, it passes the question mark through while blocking all the other bits. Now the 6th bit is really the offset of the bit that we want to modify. And this is a variable that we pass to our function called offset. Okay, now we have a new problem. We're blocking all the bits that we want to keep and passing through the 1 bit that we don't. Luckily, there's an easy fix. If we invert all of the bits in our shifted bit mask, then we get just the opposite, and only the bits we want make it through, and the 1 bit that we don't want gets blocked. This leaves us with a 1-bit hole and a 1-bit value. Of course, our value isn't in the right spot, so we have to shift it over by the offset, and then we can logically OR these two values together. And there you go. Our value is right where we want it, and we didn't change any of the other bits in the register value. Now we just need to overwrite the old register value, and thankfully, setting something equal to something else returns that something else. So this expression will actually have the value of our updated register. Why is this important? Well, instead of making this a function, we can make it a macro. Macros basically replace code that you use over and over with something that looks more like a function call. We're not going to get too deep into how this works here, but one tip, put parentheses around every variable. Okay, I know this line of code is a bit of an eyesore, and it's probably the most complicated line of code in here. But the magic of macros is you can just use that thing that looks like a function and not worry about the details of the expression. All right, let's backtrack a tick and see how we'd use it to write that vibrato function that we were talking about. Turns out you can write it in one line of code. First off, fundamentally, we know that this needs to send data to the YM3812, so let's drop that function in. Now this function needs the register location that we want to update, and to figure that out, let's go back to our register map from the first video. Okay, vibrato depth is bit 6 of register location BD. So let's pop 0xBD. The 0x is just a notation that indicates that this is in hexadecimal. Let's put that into our function. Next, the value that we want to send is just going to be the updated value of the register. And we know from our last rabbit hole exploration that this setBits macro will be equal to the updated register value. Now the first thing we need here is the variable containing the current register value, which comes from our register cache. And while I've mentioned that a few times, I've never actually described what that is. For global settings like these, the register cache is just a set of 1-byte variables, which for clarity I've named after their base addresses. So in this case, we want the variable called reg_bd. So let's pop that in here. What about the bit mask? Well, vibrato depth is just a 1-bit flag, so our bit mask should only have a single 1. And since this is bit 6, our offset should be 6. Finally, we have the new value that we want to stick into the register, and that is just the value that we've passed to the function, so no change here. Okay, let's try something a little more complicated and write one that changes a channel level property, maybe the feedback property. Going back to our chart, the feedback property sits in bits 1 through 3 of the registers C0 through C8, and each of those bytes corresponds to the 9 different channels. So to figure out which byte we want to change, we start at the base address and add the channel index. And just remember that the channel index starts at 0, not 1, so channel 1 is index 0. But yeah, we just drop this in as our register address. What about the register cache? Well, there are 3 different base addresses, and they each hold 9 bytes. So instead of having a single byte like we did for the global registers, we can keep them in separate byte arrays. Then all we need to do is pass the entry that corresponds to the channel that we're modifying and use that as our register cache variable. Bitmask works just like it did before, but it's a 3-bit variable, so we need 3 ones. And since the rightmost bit is bit 1, our offset will be a 1 as well. And that's it. That's a channel function. Now for the most complicated of all of these functions. Let's modify an operator level property like attack. Just as before, we start with our register map. And here's attack at bits 4 through 7 on base address 60. So let's do the easy stuff first. It's a 4-bit wide value, so our bit mask is going to have 4 ones. And the right-hand bit is at bit 4, so our offset is going to be 4 as well. And just like channels, our register value is going to be stored in an array, but this one will have 18 bytes because there's 18 operators. So we'll take the reg60 array and pass in the operator of interest, and then stick the whole thing into our function. Now for the tricky part. What register address do we update? To figure that out, let's look at the rest of the chart. And maybe focus on the pattern rather than the specific register address. So the first line here, 142536, etc., shows which operator corresponds with each channel. And the second line, 031425, shows the offset from the base address. For the most part, everything is in order. Operator 1 maps to offset 0, 2 to 1, 3 to 2, etc. But there are these skips where we jump from offset 5 for operator 6 to offset 8 for operator 7. And then again, there's another jump later where we skip offsets E and F. So the simplest way I've seen to get around this is to map the operator index to a register offset using an array. Then all we need to do is take our base address, add on our mapping array, and use the operator index to choose the right offset. Pop that into our function, and we're done. Now what I love about these one-line functions is that you can pretty succinctly describe all of the register functions this way, and they almost look like a table that just encodes the information from our register map, but in code form. Here are the channel ones, and the global ones. And that's really all there is to our YM3812 class. Now let's see how we can use this to make that F major 7th chord that we heard in the last video. All right, let's go back to the .ino file. This is the file that has the setup function and the loop function. So here we create an instance of our YM3812 library, and that's going to be stored in the YM3812.h and .cpp files. The .h file is going to define our class, and then it's also going to have things like the setBits function and all the register cache variables and our one-line function headers that update the global channel and operator properties. Where the CPP file is going to have the longer implementations, like the functions that need more lines of code, things like the constructor function or send data or reset. All right, let's go back to the .ino file and get this thing working. First, we need to run the reset function to make sure the chip gets reset and all the register cache variables get cleared out. Now, to make our lives a little bit easier, we're going to need a couple of integers to track the operator indexes that we're going to be modifying. All right, let's define our patch. And of course, we want this patch to sound the same for all of the channels, so let's loop through all of those channels. And instead of using 9 for like the number of channels, we can grab the number of channels from our .h file. So this way, if we migrate this code in the future to like another sound processor, then we'll have less things to tweak. And if you recall from earlier, the relationship between operators and channels is kind of a complicated one because of all that skipping. So in addition to the op map, I've also added a channel map that converts a channel index into the index of the first operator. And for now, I've made this a public variable so we can cheat and just use this in our .ino file. But in the future, we're going to fix this, so don't worry about it too much. All right, let's add our channel map here. And the second operator is always going to be 3 higher than the first. Okay, let's add some channel properties. How about we set algorithm to additive synthesis, that's a 1. And we'll set feedback to 0. And then for operator 1, let's set attack to, I don't know, how about B? What is that, 11? And then decay to maybe 6. And sustain to A, that's 10. And release to 2. Okay, and then level we'll set to 0, so it's fully on. 64 is fully off, and 0 is fully on in this case. And then for waveform, let's set this to half sine, which is waveform number 1. And then for operator 2, let's just do all of the same stuff. So we'll just cut and paste this here and then update all of these to use the operator 2 index. Okay, now we have our voice configured. Let's make it play some notes. First, we need to turn off any notes that are on by setting the key on to false. And since there's 4 notes that we want to play in our chord, we need to do this with 4 channels. Now that the notes are off, we can change the pitches of the keys, but first we want to set the octave of the note that we want to play. And we'll go with 4 here. And of course we have to do that for every channel. And now we can actually set the frequency. And this is where I'm going to leave a little bit of mystery, because decoding the frequency values in order to add MIDI functionality is going to be the topic of our next video. So bear with me and just believe me that these codes actually map to the different notes that we want to play. All right, now that we know the frequencies are all set, let's turn the keys on one at a time. But let's put a short delay in between each one so that the chord kind of rolls in. And then we can put a longer delay at the end, like maybe a second. And then we'll turn all the keys off and then back on so that everything plays together. And then let's add another 1 second delay, and then we'll just repeat the entire loop, and that'll make this whole thing play over and over. All right, let's see what this sounds like. We'll compile the code and then send it up to the microcontroller. Okay, that got pretty repetitive pretty quickly. So maybe we can mix it up and make it change over time. Okay, let's add a count variable to track how many times we've gone through the loop. And then down here, we can increment that count by 4, and then we'll make it loop back to 0 every time it hits 16. Now we need to update all the channels at the same time. So let's do what we did up above and grab that loop from up there. And then let's see, let's update the sustain property. So we can grab this line of code and drop it in down in the loop. And instead of using a constant value, let's use our count variable. And we do the same thing for operator 2 as well. Let's see, that didn't compile. Okay, it looks like I forgot to define op1 and op2 index in this function. So let's go ahead and define those up here. And now it compiles and uploads into the microcontroller. Cool, let's have a listen. So even though we're increasing the count, can you hear how the sustain is actually decreasing? That's because the sustain of 0 is actually the loudest. So what if we wanted to flip this so that over time this gets louder instead of quieter? Well, all we need to do is subtract our count from 16. So that way the setting goes from 16 to 0 instead of 0 to 16. Okay, let's try this out. Yeah, I think I like this better. Okay, I could sit here tweaking things all day. It's actually super fun, just trying to play with the properties and see what kind of voices you can make. But I think I'll leave it here and leave it up to you guys to play with some of the properties and see what kind of sounds you guys can make. And if you're able to do something cool, if it sounds awesome, post a note in the comments and I'll take a look at it and maybe try it out myself. I know we've covered a lot of content in this video, but my hope is that it gives you a strong foundation for what's to come. So namely, we're going to add MIDI control, and there's a whole bunch of stuff that we have to figure out there, like how you pick frequencies and then assign those to MIDI notes and all kinds of good stuff. So stay tuned, and thanks for watching, and we'll see you next time on